Good morning, Onadal. Let us come back to the session. Today we will be starting with BJT biasing techniques, and let us just recall what happened in the yesterday's class. And in the last class we studied the following topics: the BJT biasing, DC load line concept and its importance, bias point and operating point or the Q point, the problems on bias point, and to certain extent the circuit diagram of fixed bias we have seen. So, let us just recall the definition of BJT biasing. BJT biasing, the proper flow of zero signal collector current and proper maintenance of collector to emitter voltage during the passage of the signal. This is called as biasing. So, we took the help of DC load line to fix the operating point, which is the point which is fixed on at the center of the active region, for getting the faithful amplification. So, what is faithful amplification? All those we discussed yesterday in detail, and we also discussed on the problems of bias point and fixed bias circuit or base bias circuit we have seen. So, what are the learning outcomes of this session? We will be studying in detail the base biasing, problems on base biasing, voltage divider biasing, and problems on voltage divider biasing. So, base bias or fixed bias technique. The base bias or fixed bias technique uses one resistor, fixed large value of resistor between the VCC and the base, as shown in the diagram figure 1. So, base bias or fixed bias, the figure shows the base bias or the fixed bias. It has a fixed resistor RB between the base and the VCC point, as shown in the diagram. As I told you, a fixed resistance RB is used between the base and the supply VCC. Here the fixed constant current is made to flow in the base region, so that constant collector current is made to flow in the collector, thereby the biasing is maintained, so that we get a faithful amplification. Since the fixed resistor RB is used to determine the constant base current and hence the constant collector current is maintained, therefore, this technique is called as fixed bias or the base bias technique. Now, let us go back to that circuit. So, let us apply Kirchhoff's voltage law to the input loop, that is base emitter loop, so that we get the expression for the base current IB. So, applying KVL to the base emitter loop, we get what we get. Let us see on the board. So, the circuit is this one, fixed bias circuit. There is a resistor RB connected between the base and the VCC points. So, this is collector, this is emitter. So, when we apply the Kirchhoff's current law, voltage law to the base emitter loop here in this direction, we get plus VCC, minus to plus has been taken as positive, and plus to minus is been taken as minus. So, here the current is going in this direction IB, and IC is going in this direction. So, let us apply KVL for this. Plus to minus, minus to plus we are going. So, plus VCC minus IB into RB, minus IB into RB. Here base to emitter there is cut-in voltage which is VBE. So, minus VBE equal to 0, minus VBE equal to 0. Therefore, what we get here, we want to find out IB. So, IB is equal to, so we will get IB is equal to VCC minus VBE divided by RB. So this is the base current which we get. So let me call this as equation 1. Now I said a constant base current is made to flow in the base region, so that we get a constant collector current, so that our faithful amplification we get. So here VCC, as you know that VCC is constant and RB is a fixed value, and VBE, which is the cut-in voltage of transistor, which is a cut-in voltage of the transistor, whose value will be VBE is equal to 0.7 volts for silicon transistor, and it is equal to 0.3 volts for germanium transistor. So again this VBE is also constant. So the constant minus constant is constant divided by constant. So totally we get constant divided by constant, therefore IB remains constant. When IB remains constant and IC is given by beta into IB. We know that in a CE configuration the current gain beta or HFE, we call beta also as HFE, which is given by output current by input current, output current by input current. So output current in CE configuration will be IC, and input current in CE configuration is IB. Therefore what is IC out of this? IC is equal to beta or HFE into IB. So therefore IC is given by beta into IB. So already IB is constant here from equation 1. We substitute here, which will be multiplied with the constant value beta. IC is equal to beta times VCC minus VBE divided by RB. So this is IC. So let me call this as equation 2. So we get a constant current IB due to constant resistor RB, and since IB is constant, IC is also constant, but it depends on beta. As we know that beta varies with temperature, a slight variation will be there, but still anyway we achieved some constant current, the collector current. Since the collector current is constant and we get the when we once fix the operating point at the center of the active region for fixed bias circuit, it won't be further varied. Varied means it may not move upwards, then also we get unfaithful amplification. It won't move downwards, then also we will get a constant output. So faithful amplification we will be getting since IC is constant. Let us come back to this. So that's what, observing the above equation, that is equation number 1. Observing equation number 1, it is clear that the fixed base current is achieved using fixed bias base resistor RB. Hence this technique is called as base bias or fixed bias technique. The collector current is given by beta times IB. So it is written here beta times IB, and we get the IC is equal to beta times VCC minus VBE divided by RB. Now we also require one more value, which is VCE. So in order to find out VCE comes in the output loop. So this is the loop. As I told you yesterday, positive, the meaning of plus VCC here is positive and negative of the battery VCC. Positive is connected to this point and negative is connected to this point. Therefore there is a loop formed. And here there is plus minus VCE will be there. So we need to find out VCE. I told you yesterday in the last class, KVL plays a very important role in biasing. So let us apply KVL to find out VCE. Applying KVL to the output loop in this direction, we get, so as I told you, minus to plus I will take plus, and plus to minus I will take it as negative. It is a conventional thing. even if you want to assume in the reverse direction also. So, minus to plus you can also take it as negative, plus to minus you can take it as positive. Therefore, applying KVL to the output loop, what we will get, we will see plus VCC minus IC into RC minus VCE is equal to 0. So, what is VCE out of this? VCE is equal to, it is plus VCC minus IC RC. So, this is the equation for VCE. Why I found out IC and VCE? Because the operating point or the bias point or the fixed point is an ordered pair of IC and VCE. So, IC is given by beta VCC minus VBE by RB, which is equation 2, and VCE is given by VCC minus IC into RC. So, that is VCE. So, I have found out VCE and IC. Therefore, I can easily write the operating point Q. Now, let us come to equation number 3. As we have proved that from equation 2, IC is constant, so maybe some small variation, but it is constant. Now, since IC is constant, RC is a fixed value, VCC is a fixed value, therefore, VCE is also fixed. Therefore, IC and VCE both are fixed. IC and VCE both are fixed. Therefore, we achieve constant or stable operating point at the center of the active region, which will not be affected. But we will see what are the disadvantages of fixed bias technique later, right. So, as I showed here in the PPTs, applying KVL to the output loop, we get VCC minus IC RC minus VCE equal to 0, which gives us VCE equal to VCC minus IC into RC. As IC is constant and RC is constant and VCC is also constant, equation 3 is given by VCE is equal to VCC minus IC RC, therefore, VCE is also constant. So, we got IC constant, VCE constant. When IC and VCE are not varying, when once we fix the operating point, IC and VCE will not vary, means the operating point which is fixed at the center of the active region is constantly fixed there, or we can say it is stable there. When once we get the stable operating point, we get the faithful amplification. But there are certain disadvantages, we will see that later. Thus, using equations 1, 2 and 3, we can design the fixed bias circuit and determine the Q point, Let us take one numerical problem on fixed bias or the base bias. Determine the Q point for the following base bias circuit with VCC is equal to 8 volts, RC is equal to 2 kilo ohms and RB is equal to 360 kilo ohms. So, as I told you, RB will be usually a very large value. A very large fixed value is used to maintain very small base current IB, constant base current IB. Therefore, we get constant IC and we achieve constant operating point, which is fixed at the center of the active region. And here they have given VB is equal to plus 0.7 volts. What is the transistor used? The transistor used is silicon transistor, because VB is equal to 0.7 for 7 volts for silicon transistor and VB is equal to 0.3 for germanium transistor. Suppose if VB is not given in the problem, we can always assume silicon transistor, therefore, VB can be taken as 0.7 volts. So, let us move with this. So, as we know that IB is given by VCC minus VBE by RB, therefore, substituting the values here, 8 volts minus 0.7 volts, which will be divided by 360 kilo ohms will give us, if you calculate this value, 20.28 microamps. IB will be usually in microamps, which will be a very small value. So, IB is equal to 20.28 microamps. Let us find out IC. IC is given by HFE into IB. As I told you, HFE and beta both are same. with different notations, that is all. So, it is a DC current gain in the CE configuration, which is given by IC by IB. Therefore, IC is equal to beta or HFE into IB. So, here in this given problem, HFE is given to be 100 and IB we have calculated, which is 20.28 microamps. Therefore, if you calculate this value, it comes out to be IC is equal to 2.028 milliamps. Next, VCE, we need to find out VCE. So, which is given by VCE is equal to VCC minus IC RC. Therefore, VCC we know 8 volts and VCE we know 8 volts. It is 8 volts minus IC is 2.028 milliamps multiplied by 2 kilo ohms. We get VC is equal to 3.94 volts. So, what is the operating point? We obtained IC value and we have obtained VCE value for this problem. The operating point or the Q point of the above problem will be an ordered pair of Q, ordered pair of IC and VCE, which is represented by Q. Q is equal to 2.028 milliamps, 3.94 volts, which is the operating point for the given problem. Next topic of base bias will be what is the effect if we change the beta or the HFE values. Why we have to change the HFE or beta value, HFE maximum and minimum we are taking as an example. So, this beta or HFE is keep on changing with respect to temperature. Now, here HFE min is nothing but beta min. HFE min is nothing but beta min. As I told you, HFE and beta both are same. So, here HFE min is nothing but beta min. I will write here HFE min is nothing but beta min. Next, HFE max is nothing but beta max. So, what is the effect of operating point in fixed bias or the base bias when we change the HFE values from minimum to maximum? That is the discussion now. So, when the transistor DC current gain is known, then it is very easy to determine the circuit bias conditions exactly. So, that is true only. When the DC current gain, that is beta or HFE is known, we can easily find out IC for the fixed bias circuit, and then we can easily find out VCE, and then we can fix the operating point at the center of the active region, so that we get the faithful amplification. But usually, however, in practice, the precise current gain for each transistor is not normally known, because it is a temperature dependent parameter which we may not be knowing, but we will be knowing the maximum and minimum values from the data sheet of the transistor. So, the transistor is usually identified by its type, the minimum and maximum values of current gains, which can be obtained from the manufacturer's data sheets, say data sheet of the BJT. So, what is the problem if we change the beta to from minimum value to maximum value? So, for discussing this, let us consider problem, which is problem to study the effect of HFE max and HFE min. For a biasing circuit, HFE max effect and HFE minimum effect will be very important, so that we can decide something whether the bias circuit is good and it is giving a faithful amplification or not, we will be studying. So, for getting the faithful amplification, we must have a minimum change in the operating point if we change the HFE min and HFE max. If we consider HFE min and HFE max, there should be minimum change. Let us see with this problem. Let us take the problem and study what is when HFE min is something minimum value, what is the operating point. When HFE max is some maximum value, what is the operating point. Let us study that through this problem. So, the problem is calculate the maximum and minimum levels of IC and VCE for the base bias circuit of figure 1. So, we have shown the figure 1 is already written on the board. This is the figure 1, which in the previous slides I have considered. So, that is this is figure 1. So, this is figure 1. So, this is the figure 1. So, figure 1 is a fixed bias circuit, and for this circuit what I will do? I will change the HFE values from minimum to maximum, and I will study what is the performance with respect to the operating point Q. Yes. Calculate the maximum and minimum levels of IC and VCE for the base bias circuit of figure 1 shown above when HFE min is 50. Now, the HFE min value is 50, that is beta min, and HFE max is 200, right. Now, the base current in both the cases will remain same, because it is not dependent on beta or HFE min or max values. So, the base current IB is given by, we know that base current IB is given by IB is equal to VCC minus VBE by RB, and in this problem VCC is 18 volts and VBE is 0.7 volts and RB is taken as 470 kilo ohms. So, therefore, IB is found to be 36.8 microamps. Now, let us consider case 1. Case 1 with HFE is considered as minimum value, which is given to be 50. Now, IC is equal to HFE min into IB. So, we know that IC is given by HFE min or beta min into IB, therefore, which is 50. Beta is 50 now, and IB we have calculated, which is 36.8 microamps. Therefore, we get IC is equal to 1.84 milliamps. IC is equal to 1.84 milliamps. And similarly, VCE we need to find out, which is given by VCC minus IC into RC, which is VCC is 18 volts in this problem, 18 volts minus IC into RC. So, which is 1.84 milliamps into 2.2 kilo. Therefore, VCE, if you calculate this value, it is found to be 13.95. So, this is case 1. For case 1, HFE is taken as minimum value, which is 50 is given in the problem. So, for that I have found out what is IC, which is 1.84 milliamps, and I have already found, I also found out what is VCE, which is 13.95 for this problem. Next, case 2. Case 2, what is case 2? We consider beta as maximum value now. So, for HFE max equal to 200, we need to again find out IC and VCE values, so that we can compare when beta is 50, what is the operating point, and when beta is 200, what is the operating point. That is the study of effect of HFE max and HFE min. So, case 2, for HFE max is equal to 200, what is the value of IC? So, IC is given by, again, in place of HFE or beta, we will write HFE max and into IB. So, HFE max is given to be 200 and IB we found out already, it is 36.8 microamps. Therefore, the value of IC will be 7.36 milliamps in this particular case. All of you should find out these values and check by using a calculator. Right here directly I have done and kept the answers, and VCE is given by VCC minus IC into RC, which is 18 volts minus 7.36 is the collector current which we got for HFE is equal to 200, which is multiplied by RC, which is 2.2 K. Therefore, VCE now, the new value of VCE is 1.8 volts. 1.8 volts. Now, let us compare the values with the circuits. So, figure 2a conditions of the circuit for HFE min is equal to 50. Figure 2b gives us conditions for HFE max equal to 200. Circuit conditions of for HFE max equal to 200. If we can clearly see here, that IC when HFE was minimum, IC is found to be 1.84 milliamps, and when HF in case 2, this is 200. So, we have taken HFE max as 200. For HFE max as 200, we get IC is equal to 7.3 milliamps. See, there is a large change in IC from 1.84 milliamps to 7.36 milliamps when we just change the beta value or the current gain of the BJT from minimum value to maximum value. What happens in the case of VCE? So, in case of VCE, when beta was minimum, VCE was found to be 13.95 volts, and when beta was maximum, the VCE was reduced to 1.8 volts. So, if we can observe this change, a large change is there in IC and VCE values. Therefore, if we change the beta value in case of fixed bias or the base bias, the operating point shifts uncertainly. That is the conclusion out of this. Let us see what is the conclusion. Now, problem to study the effect of HFE max and HFE min. This is the graph which is taken from David A. Bell book, and here we have marked the operating points for both the cases. For HFE minimum, so operating point is here. For HFE max, the operating point is here, and we also taken HFE equal to 100, and we have calculated that comes somewhere here. Here. This point, these 3 points. Now, if we see this graph, the transistor HFE value has a major effect on the Q point for the base bias circuit. There is an uncertainty in the operating point. When there is an uncertainty in the operating point, we may not get the faithful amplification, we always get unfaithful amplification. That is the major disadvantage of fixed bias circuit. So, what is the inference? The inference here is the HFE max and HFE min should always be a practical circuit analysis, should always be used for practical circuit analysis. So, we saw that IC was fixed, which is a constant, and VCE was fixed, which is a constant for a base bias circuit. We got constant or the stable operating point just by the theory analysis, and when we change HFE values or beta values from minimum to maximum or vice versa, we got the uncertainty in the operating point. So, that is a major disadvantage of fixed bias circuit. Here in figure 3, that is a graph which we have shown previously. So, this graph. So, figure 3 is the graph. So, in figure 3, it is clear that the base point is not stable, bias point is not stable. If there is a major change in the current gain in base bias, as there is a major change in the current gain. If there is a major change in the current gain, that is we have taken 50, 100 and 200 values, and if there is a major change 50 to 100, 100 to 200, then bias point is not stable. That is the inference out of this discussion. The base bias is rarely employed. Why? Because there is a uncertainty in the Q point. So, the base bias is rarely employed because of uncertainty in the Q point. This is the disadvantage of base bias technique. So, base bias technique cannot be used as a efficient biasing technique for biasing the transistor for getting faithful amplification. So, this is the conclusion out of this. Now, let us move on to voltage divider bias circuit. Voltage divider bias circuit, which is widely used type of biasing circuit. The only one power supply is needed and the voltage divider bias is more stable, and it is, we will show that later by taking one problem. The beta independent voltage divider bias technique is beta independent, like unlike other types of biasing techniques. So, let us move to board and we will study what is this voltage divider bias circuit. Before going to voltage divider bias technique, what is voltage divider biasing? What is voltage divider network? Let us see. So, the voltage divider network, when we come across this type of network in any time when we come across this type of network, there is a VCC, let us say here. This is R1 and this is R2. At this point, the voltage, let me call it as VB. At this point, this entire network is a voltage divider network. Voltage divider network. Let us see why it is called as voltage divider network. So, at this point, the voltage gets divided, VCC gets divided by some value. We will see what is that value. Because of this reason, we call this network as voltage divider bias circuit, voltage divider network. Actually, when we come across this type of circuit, we need to apply the Thevenin's theorem. Right now, for the first year students, Thevenin's theorem is not suggestible. So, I will give you very best and simple formula for finding out at this midpoint of resistors, which is VB. So, what is the formula here? VB is given by, you just remember this formula, applied voltage. That formula is obtained by applying Thevenin's theorem, right. So, applied voltage multiplied by grounded resistance. I will write here grounded resistance, grounded resistor. This entire thing divided by sum of resistors. Actually, we need to apply Thevenin's theorem. And we will be arriving, when we apply Thevenin's theorem for this circuit, we will be getting this expression. Actually, Thevenin's theorem is not included for first year students. When electronic students comes to third sem, the electronic related branches, they will be studying Thevenin's theorem. Again, these circuits will be revisited in analog electronic circuits, which is in third semester. Let us not worry about all those. So, VB is given by a simple formula here, applied voltage multiplied by grounded resistor divided by sum of resistors. So, here applied voltage is VCC. Here the applied voltage is VCC and the grounded resistance is R2. These two we need to multiply and we have to divide that multiplied value by the sum of R1 and R2. Therefore, let us write what is VB. VB is given by applied voltage, which is VCC, multiplied by the grounded resistance R2, that is R2, divided by the sum of resistors. So, R1 plus R2. So, this is the voltage VB. So, VB is given by, we can write VB now as this R2 can be taken to the denominator. Therefore, VCC gets divided by R1 plus R2 divided by R2. So, this value. Now, why this is called as voltage divider network? Voltage VCC, which is the applied voltage to the network, is getting divided by some value, I told you, right. That is the value, that is R1 plus R2 by R2. Therefore, VCC gets divided by some value and that value is given by R1 plus R2 by R2. Therefore, this network is called as voltage divider network. And since we use this network in our biasing technique, along with the transistor, therefore, it is called as voltage divider biasing. Let us come to these PPTs. So, what is voltage divider biasing technique? DC bias voltage at base of the transistor. The DC bias voltage at base of the transistor is developed by a resistive voltage divider consisting of R1 and R2. This is the circuit. So, voltage divider network consisting of R1 and R2, and this is connected to base of the transistor, and this will be connected to the base of the transistor. Therefore, the base voltage is supplied by this network. Therefore, it is called as voltage divider biasing. Hence, the name voltage divider biasing for the biasing circuit. So, here I have considered draw the Thevenin's equivalent circuit, write the necessary KVL KCL equations, determine the quiescent point. All these are applicable to one technique of voltage divider bias technique, which is a precise voltage divider bias network circuit. We will see that later, right. When we consider voltage divider biasing technique, there are two ways of analyzing the voltage divider biasing network technique. The voltage divider bias circuit can be analyzed in two different ways. They are, one is approximate circuit analysis. Approximate circuit analysis. For simplification purpose, we consider this approximate circuit analysis. As the name tells you, it is an approximate analysis and it is not the accurate analysis. Accurate analysis means we need to go for a precise technique, which is the second technique. We will see that later. So, first technique we will study through the voltage divider bias circuit. We will have to analyze the voltage divider bias circuit by approximate analysis. Let us consider this voltage divider bias approximate analysis. So, how the voltage divider bias circuit looks like? The voltage divider bias circuit looks like this. I will rub off this. This is same R2, R1, and this VCC I will connect in a different manner now. This is given to base of the transistor, and there will be emitter resistor RE through which the current IE is flowing. Then there is a collector resistor RC. R1 is connected to VCC in this way. This is plus VCC. Plus VCC. IC is flowing in this direction, and this is the collector point, this is a base point, base B, this is emitter E. Now, since I used this network, even you can connect this is a ground, therefore, we can connect these 2 points, right. Now, to bias this transistor, we used a network called as voltage divider bias network, therefore, it is a voltage divider biasing technique. Voltage divider bias circuit or network, both are same. Voltage divider bias circuit. So, that is what is shown in the PPT here. So, this is a voltage divider bias circuit, wherein this acts as a voltage divider network. This is a voltage divider network. So, the base is connected by the voltage divider network, therefore, it is called as voltage divider biasing. And for approximate analysis, we will be assuming that IC is approximately equal to IE. IC is approximately equal to IE, right. So, in the approximate analysis, we will be considering this as VE, and of course, there is plus minus VCE here, and at this point whatever the voltage with respect to ground we get, it is called as VC. This is VC, and of course what voltage is flowing through RC? It is IC into RC. We know that current multiplied by resistance gives voltage, that is the drop in the RC, and this voltage between base and the ground we call it as VB, and the current I2 is flowing in the R2, and the base current IB is flowing through the base. So I is flowing here, the voltage in this RE is VE, which is given by IE into RE. So let us now consider the approximate analysis. In the approximate analysis, we will consider the base voltage with respect to ground as VB. The base voltage VB can be considered with respect to ground, which is VB, and the emitter resistance VE we will be considering from the emitter to the ground, from the emitter to the ground, from the emitter to the ground, and VC, the collector voltage, we will consider it as it from collector voltage, from collector to the ground, whatever the voltage is there, which we will call it as VC. And IE is the emitter current, IC is the collector current, and I2 is the voltage divider network current. When we can, my question is, there are two analyses here. One is exact analysis or the precise analysis. The other one is the approximate analysis. When to use approximate analysis and when to use precise analysis. So this is approximate analysis. We will approximate here as IE is approximately equal to IC. So this approximation we will be using in the approximate analysis. That is one point. The other point is IB, the base current IB, if it is less than the voltage divider network current I2, I repeat this, the base current IB is less than the voltage divider network current. So I2 is a voltage divider network current. When IB is less than I2, then we will be going for the approximate analysis, and that will be correct only, right? So IB less than I2, one condition. The other condition is we will approximate IC is equal to IE or vice versa. In only under such case we can go for the approximate analysis. Let us come to this. Now in approximate analysis, VB can be assumed to be constant. VB can be assumed to be constant and is given by VB is equal to VB, as I told you, it is a voltage divider network current only, voltage only. At this point, what is the voltage? Which is VB, I have written in the last I have written, that is applied voltage VCC into R2 grounded resistance divided by R1 plus R2. So this is VB. So VB is assumed to be constant. Why we have to assume? VCC is constant, R2, R1 both are constants, fixed values. So when you divide any fixed value by any other fixed value, it is only a constant. So VB is assumed to be constant in the approximate analysis. The 3 points you must remember here in approximate analysis: the base current IB is assumed to be very small when compared to voltage divider network current, and IE is approximated to IC. The other point, the next point is VB, the voltage at the base terminal with respect to ground, which is VB given by VCC R2 divided by R1 plus R2 is assumed to be constant, and we therefore find out the further values, right. Next, so that point is indicated by this. So VB is given by VCC R2 by R1 plus R2, which is equation number 1. Therefore, VE, what is VE? Let us see what is VE. Where exactly VE comes here? VE comes here in the emitter circuit. So VE we need to find out. To find out VE, the current voltage here is VB, and here there is a plus minus VB cut-in voltage, which is understood, right. We will apply KVL for this loop. We will apply KVL for this input loop, lower part of the input loop, right. When we apply KVL for this input loop, what we will get? It is VB minus plus, minus to plus we will assume it as positive, as I told you. So, it is VB plus VB minus VBE minus the voltage here in this resistor is VE. Let me write VE equal to 0. The algebraic sum of voltages in a closed loop is 0, that is KVL. So, what is VE? VE is, it is IE is flowing through RE and RE is there. So, RE into IE is VE, therefore, plus VB minus VBE minus IE into RE. Therefore, what is VB from this? VB is equal to, what is IE? We need to find out now. So, what is IE from this? IE is equal to VB, which we have already found out, that is equation 1, VB minus VBE, which we know that VBE is a cut-in voltage, and if it is not given, we will assume that VBE as silicon transistors VBE, which is 0.7. So, which is constant again, divided by RE. So, this is the value. Let me call this as equation 2. So, IE is given by VB minus VBE divided by RE. Now, so V is given by VB minus VE here. One equation, I have not written that. V is equal to VB minus VBE. This is one equation. Let me call this as equation 2, and IE let me call it as equation 3. So, that is what is shown in the next slide. From the figure 4, applying KVL to the lower part of the input loop, we get VB minus VBE minus IE RE equal to 0. Therefore, IE is equal to VB minus VBE by RE, that is equation 3. Again, we need to apply KVL for the output loop, as time is going to up. So, let us continue this in the next class. And what we did today we studied the fixed bias in detail, and we have already studied what is the effect of changing the HFE or the current gain from minimum value to maximum value. We have taken three different values. From figure 3. Let us say figure 3. What is figure 3? So, this is figure 3. In figure 3, we have shown three different operating points here, and operating point is uncertain in this case in fixed bias. Therefore, fixed bias is uncertain, and it cannot be used as a biasing circuit, because the operating point is keep changing enormously with the changes in HFE or the beta values when we move from 50 to 100 and then 100 to 200. So, then we entered into voltage divider biasing. From voltage divider biasing, why it is called as voltage divider biasing? We have used voltage divider network to bias the transistor, therefore, it is called as voltage divider biasing. And in the voltage divider biasing analysis, there are two analyses. One is the approximate analysis. To certain extent, we understood what is approximate analysis. In approximate analysis, we always assume IE approximately equal to IC, one thing. The other thing is we assume that the base current of the transistor, which is used in the voltage divider bias network, is very small compared to voltage divider network. Then we can easily use the approximate analysis, which is very easy analysis compared to precise analysis. And also we assume that the base voltage VB is assumed to be constant and which is given by VCC into R2 applied voltage. That formula you must remember. Please remember this formula, which is very important in the analysis of voltage divider bias network, both in precise and approximate methods. Now, what is that formula? Let us recall that and close the session, right. So, what is the voltage divider network voltage, which is given by VB is equal to applied voltage into grounded resistor divided by sum of resistors, and which is found to be in our example VB is equal to VCC R2 divided by R1 plus R2. So, we have already we also found out equation number 2, VE is equal to VB minus VBE, and also we have found out from that equation IE is equal to VB minus VBE by RE. So, at this point we will stop today, and tomorrow's session we will continue the same analysis, and we will also study the precise analysis of voltage divider bias network. We will compare when we change the beta values or the HFE values, what happens to the stability of the operating point in voltage divider bias network. I already told one point in the beginning that voltage divider biasing network is most widely used. Why it is most widely used? I will be proving that with the help of operating points. So, with this we will close the session. Thank you very much. Thank you.